In this video, we're going to introduce the concept of slope, and we're going to look at our first form of linear equations, slope-intercept form. Before we talk about slope, we want to talk about this idea of a rate of change. The rate of change is the relationship between two quantities that are changing together. Rate of change is always going to be defined as the change in the dependent variable, or your change in y, and we'll use that little delta to represent change, over the change in the independent variable, or the change in x. It's always y over x, just like when we did direct variation, y over x. So here we have a table showing the distance a band marches over time. We want to know, is the rate of change constant? Anytime we're talking about linear functions, our rate of change is constant. That means we're changing by the same ratio of change in y to change in x. And then we want to know, what does that rate of change represent? So we're going to look for our change in y over our change in x. So as I go from 1 to 2, my change in x is 1. And as I go from 260 to 520, my change in x is going to be 260. So my change in y is 260 over 1, or 260. Now we want to check it for the next transition to see if that rate of change remains the same. So again, we're going from 2 to 3, which is a change in x of 1, and we're going from 520 to 780, which is a change again of 260. So we have 260 over 1, which is a rate of change of 260. Now we check the last one, so our change in x again is going to be 1. Now we look at our change in y. We go from 780 to 1040, and that again is a change of 260. So our change in y over our change in x is 260. So it is a constant rate of change, which means this is a linear relationship, and that rate of change means that they march, let's see, we don't have a unit, we'll say feet? I don't know, they're moving pretty quickly. They're a very speedy marching band. The band marches 260 feet in 1 minute. We're at a rate of 260 feet per minute. So when we talk specifically about linear functions and the graph of a linear function or the equation, that rate of change is called slope because it talks about the steepness of the line. So again, we have that change in x, change in y idea, and when we're talking about the coordinate plane, change in y can be represented as vertical change because that's our vertical axis, and then change in x is our horizontal change along the x-axis. We also use rise and run when we talk about those changes. Rise is our movement up and down. Run is our movement not up and down also, side to side. There are 4 different types of slope that we'll encounter. We have a positive slope. When we're going from left to right, we're increasing. Negative slope, when we're going from left to right, we are decreasing, so we'd be going downhill. We have a slope of 0, where we're not really moving at all. It's just a flat horizontal line. And then an undefined slope, when we have our vertical line. So, if we want to find the slope from a graph, the first thing we need to do is identify 2 points. The cool thing here is it does not matter which 2 points you pick. As long as you pick points that are easily distinguishable on your graph, so they go where the grid lines intersect, you can find your slope. So we start with our rise. Here to get from one point to the next, we rise 1, and then we run over 6 units. So my slope is 1/6. We're always going to leave slope as a fraction. Usually the only time we'll see decimals is when we're working with word problems, but because we want to see that specific rise and run, the fraction is going to be much more helpful. If the fraction can be reduced, we always want to make sure we reduce it. We can do the same thing here, going from the left to the right. And now, since we're going down, we're going to represent this as a negative rise. And we're going to do our run, which is positive 3. So we have negative 1. Now, say I went backwards. And we had a rise of 3. Now when we go to the left, this is going to be a negative run. So we would have 3 over negative 3, which still gets us negative 1. So truthfully, it doesn't matter which way you go. Usually we prefer to go left to right just because that's our standard way of doing things. But if you go the other way, the signs on your rise and run will flip, resulting in the same slope. here are our two special slopes. If we look at these 2 points, as we go from the left to the right, we don't move up or down at all, so my rise is 0. Then between the two that we've marked off, our run is 4. So here we have a slope of 0. This is our horizontal line. If we look at our second line here, we can go up or down, it doesn't matter. Say we go down. We have a rise of -2, but then a run of 0. This is a problem. We can't divide by 0. So our slope is undefined, and we actually have to make sure that we write or say undefined. We can't leave it as -2 over 0. We need to call it an undefined slope. We're not always going to have the graph. Sometimes we're going to have two coordinate pairs, and we want to find the slope of the line between those 2 points. This is where we're going to use our formula here to calculate the slope. It comes back to that change in y over the change in x, because when we take the difference of two values, we're truthfully still finding that change. It does not matter which point you designate as x1, y1, and which point is x2, y2, as long as you're consistent. So if we look at our first question, if this is going to be x1, this point has to be y1. And if this coordinate is x2, this one has to be y2. That order has to be consistent. So I just substitute everything into my formula. So we have -18 minus -3, and then 3 minus 2. So we have -15 over 1, which is just a slope of -15. Say we use the points in the opposite direction and we flipped it around. We would have -3 minus -18 all over 2 minus 3. So we get 15 over -1 and -15. So again, it doesn't matter which order we subtract in as long as we're consistent top to bottom. Pause the video, see if you can find the slope between 3,2 and 5,2. Here we end up with a slope of 0. We can tell this by looking at the two ordered pairs because they both have the same y coordinates. That means there's no vertical change, only horizontal change, which means that we have a slope of 0. And we're always going to simplify that out to just the integer 0. We're never going to leave it as the fraction 0 over 2 because that's technically not simplified. We can use our slope formula to answer questions like the next one. We have two coordinate pairs, but one of the coordinates is missing. And we know that the slope of the line through these points is 4. I can use my formula to set up an equation that I can then solve for the missing value. If my slope is 4, instead of writing m equals and then my formula, now we're going to say 4 equals. We put in our coordinates, we have -7 minus 9 all over y minus -15. And now we can just go through and solve. So we're going to have 4 equals -16 all over y plus 15. And now since y is in the denominator, we're going to multiply both sides by y plus 15. So we have 4 times y plus 15 equals -16. And now we just go ahead and solve this out. So 4y equals -76, which means that y is going to be equal to -19. Alright, so now that we know how to find slope, our m value, we can write equations of lines in slope-intercept form. And this is the first of 3 forms that we are going to look at. This is one of the easiest to use. It's the easiest form to use when you're going to graph an equation. We'll look at another one next time that's also really easy to use for graphing. But this is where we start just because it's this most simple form that we have. M, as we said before, represents the slope, and this constant on the end b represents the y-coordinate of the y-intercept. So if I look at my graph here, the first thing we want to do is identify the slope. So I have my 2 points, and if I'm moving between those 2 points, I have a rise of -4 and a run of 3. So my slope is going to be -4 over 3. Now I need to find the b part. So b is my y-intercept. So I look and see where my graph intersects with the y-axis, and I see that this happens right here at -2. So b equals -2. Now we just go ahead, substitute everything into our equation. So we have y equals, the only thing we replace is our m and b. So we have -4 thirds x plus -2. Now, we're never going to leave two signs next to each other like this, so we're going to reduce this and say y equals negative 4/3 x minus 2. And this equation represents this line. If I were to substitute this into my calculator, it would give me a picture that looks just like this. If I were to plug in x values, I would get all of the corresponding y values for the points along this line. So, go ahead, pause the video, and see if you can write the slope-intercept equations for the first two graphs that we have here. Alright, if we look at our graph on the left, we have between those two marked points a rise of 3 and a run of 6, which reduces to a slope of 1/2. Our graph cuts through the y-axis at the point 0, -1, so our b value is -1. We put it all together, we get our equation of y equals 1/2 x minus 1. If we look at the second graph, we end up with a slope of 4, and this graph actually cuts through the origin, just like our direct variation. So if we look at our equation, it looks like that direct variation equation. My y-intercept is 0, so we could write plus 0 on the end, but that's something extra that we don't need to include because plus 0 is not going to make any changes. So when we talked about the direct variation equations, they were really all in slope-intercept form, but because the y-intercept was 0, we didn't have that constant being added on at the end. Now, if we look at these two lines, these are our special lines. On the left, we have that undefined slope, so I can't really say that y equals undefined times x plus, oh, and I don't have a y-intercept either, so that's not going to work. If we look at this one on the right, my slope is 0, so we have y equals 0x plus 1. That's going to look a little weird. So anytime we have strictly horizontal or strictly vertical lines, our equations are going to be different. If I think about all the points on this vertical line, the one thing that they all have in common is their x-coordinate. The y-coordinate changes, but the x-coordinate remains constant for every single point. In this case, the x-coordinate is 1. So because that's what they all have in common, this is the equation for this line, x equals 1. If we look at our line over here, the x-coordinates are changing, but the y-coordinate remains the same. For every single point here, the y-coordinate equals 1. So our equation would be y equals 1. There's an acronym that we can use to help us remember the information for these special slopes. And this is going to be HOY bucks. Shout out to Sophia H. for sharing this with me, since I had not seen it before. If we look at the first part, HOY. H stands for horizontal. The O stands for 0 for our slope. And the Y means that our equation is going to be y equals. If we look at the VUX part, V is for vertical, because it's a vertical line. The U is our slope of undefined. So we'll put undefined. And then X is our equations that start with x equals. So, if I wanted to graph a line, slope-intercept form is really nice because I have all the information that I need right there in front of me. If I have my slope of -2/3, this means I can use it as we go. Remember that it doesn't matter if you put the negative in the numerator or the denominator, just pick one place to use it. And then we have our y-intercept of 1, which means we're going to plot the point 0, 1. So this is where we start, because that's the first point that we know is on the graph. So we start at 1, and now I use my slope to plot the rest of the points. My numerator is my rise, so my numerator is -2, which means I go down 2, and then I run 3 points to the right. I go down 2, and since I run out of room, I don't have to plot the point down here. Then if we want to go backwards, we're going to do the opposite of what we see. So instead of -2, I do +2, and instead of 3 to the right or +3, now we go 3 to the left, or -3. I can repeat the process, but I run out of room, so that's all I have to graph. So then I connect my dots, put our arrows on the end, and our graph is complete. Go ahead, pause the video, see if you can identify the slope and the y-intercept and any other points that might be on this graph. Alright, so if we look at this equation, we have a slope of -3, which is the same thing as -3/1 or 3 over -1. I don't have a y-intercept written down, so that means that my y-intercept is 0, or the origin. So we start in the middle of our graph, we rise our -3, we run 1, then we go backwards, we rise +3 and run -1. Now the last thing that we want to be able to do is to write an equation in slope-intercept form if we're given 2 points. So here we need to figure out our y-intercept and our slope. Luckily we have a formula that gives us slope. So we have the difference in y's divided by the difference in x's. So I can go ahead and I can start with that. So I have my second coordinate here, so 4 minus 2 all over 0 minus negative 4, which is 2 over 4, or 1/2. So I have half of what I need. I need to fill in that y-intercept. If I look at my points, here I have an x-coordinate of 0. That means that this point sits on the y-axis. So that means that my y-intercept is 4. So we don't have any extra work to do. This one's nice and easy because we get our y-intercept right from the information that's given. However, if you look at the second question, you can see that we're not always going to be given that point. So sometimes, ignore the bell, we have to do a little bit of extra work. We still start in the same place. We start with our slope. So we have 2 minus negative 1 all over negative 1 minus negative 4. When you're working with the slope formula, it's really important to be careful with your signs because you are going to have to do some subtraction with the negative. So you just want to be careful, make sure you don't lose anything. So we have 3 over 3, which is a slope of 1. Now we need to find our y-intercept. So if I look at my equations so far, I have y equals 1x or just x plus b. We need to solve for this b value, which means that we need numbers that we can substitute in for y and x. If I look at my coordinates, I have two sets of values that I can use. I have two pairs of xy coordinates. It does not matter which one you pick. I can go with the first point if I want. I'm going to take these values and substitute them into my equation, so that way I only have one unknown and I can solve for the y-intercept. So we're going to say that negative 1 equals negative 4 plus b. Add 4 to both sides, and we get a y-intercept of 3. So now we can write our full equation, which is y equals x plus 3. Anytime the y-intercept is not one of your coordinate pairs, you have to take the second step of solving for b. You can't just randomly put a number in. You have to show this out that you have algebraically proved that that is your y-intercept.